It is my pleasure to introduce today's keynote speaker, Dr. Maria Uriarte. She's professor and chair of the Department of Ecology, Evolution, and Environmental Biology at Columbia University. Dr. Uriarte is a leading tropical ecologist whose research focuses on forest recovery, biodiversity, and the impacts of natural disturbances, such as hurricanes, droughts, and fires. She has authored nearly 200 peer-reviewed publications and mentored dozens of graduate students and postdoctoral researchers. Her work is widely recognized and has been featured in major media, including the New York Times and CNN. Today, Maria will speak about compound disturbances in tropical ecosystems, how interacting and sequential stressors are reshaping forest dynamics under climate change, and what this means for conservation and management. Her talk will draw on compelling case studies from the Amazon, the Caribbean, and Southeast Asia. Please join me in a welcoming for Dr. Maria Uriarte.
Okay, can you hear me now? Great. So first of all, I'd like to thank the organizers for inviting me and to give me an excuse to think about a lot of things that I've been thinking about for many years, and to try to make some sense and put them together. And this is the issue of compound disturbances and what they mean for tropical ecosystems. I'm going to start with some definitions, just to make sure that we're all on the same page, and that we mean the same thing when we say disturbance. Then I'm going to talk about why we should care about compound disturbances. I'm going to illustrate a bunch of case studies that we have observed of compound disturbances in the tropics, with a focus on moist tropical forest and also on the neotropics, but the issues that I'm going to discuss apply widely in the tropics. They're not constrained to a particular ecosystem or to a particular region. And then I hope I can offer some suggestions on how to move forward and the big critical knowledge that we have in this area. So what is a disturbance, right? This is a basic question. And generally, we think of a disturbance as something that causes an abrupt change in an ecosystem. And this could be loss of biomass. It usually means that some trees are killed. It usually means that we have a change in the species composition. And these are caused by multiple disturbance events like floods, fires, hurricanes, insects, and so forth. The combination of disturbance agents and the frequency and severity of disturbance events is what we call a disturbance regime. We also distinguish between natural disturbance agents, and these are things like I just mentioned, fires, floods, hurricanes, and another thing that we call anthropogenic disturbance, which is human land use of all types and the introduction of new species. What is very clear is that these events, both natural and anthropogenic, have major consequences for biodiversity, ecosystem structure, land-atmospheric interactions, and ultimately human well-being. So disturbance typically leave some kind of legacy in the ecosystem. They could be structural, things like dead trees standing, caused with debris, by geochemical legacies of things that go into the soil. And these are the legacies that mediate the resilience to disturbance. If a particular ecosystem biota eventually will develop evolutionary help to provide resistance to disturbance. Interactions developed when these legacies are functional. The resistance of the ecosystem to a subsequent disturbance or the resilience. So let me illustrate this in this very nice paper from Tomás Ibáñez. So we can have two disturbances that don't interact. Supposed to hold this, but anyhow, on the top left-hand corner, we can have two disturbances that don't interact at all. You can have a disturbance that causes an increased likelihood of another disturbance, for instance, a hurricane. If the dead biomass dries out, will increase the likelihood of fire. It can also lead to increased severity of a disturbance. In the same case, if a fire were to happen in a forest for a cyclone, it would be a lot more severe than if it had not. It could delay the recovery for the same reason. If a forest that had been affected by a cyclone, if hit by a fire, it will take longer to recover. And ultimately, in the most severe of cases, we have ecosystem shift. That means that the ecosystem does not return to the same state it was in. And by a state, I mean biomass, species composition, structure, whatever it is that you want to think about. The sequence matters. So a fire before a hurricane is not the same as a hurricane before a fire. And I'm going to discuss some of those cases. Why do we care? Well, I think everybody in this room knows that all kinds of natural disturbances are increasing in frequency and severity. In the last decade, a number of hurricanes that have surpassed anything that we have seen in the last couple of 100 years in terms of severity, the last one in 2017. Fires are increasing everywhere. When you look at boreal forests, temperate forests, insect outbreaks, and so forth, everything is increasing with climate change. And at the same time, we have anthropogenic disturbance, right? The proportions of forests that are in some stage of regrowth after human cultivation or degradation is right now, the latest estimate, 17%. And one of the biggest climate drivers is the temperature of the ocean. That last year, 2024, globally in the ocean with now it works very high, and then it cooled off in the summer. But this particular, the ocean, of course, has absorbed the majority of human-caused global warming. About 90% of the heat is absorbed by the ocean. And this suggests that there may be some limits to what the ocean can absorb. And last year, the drought that was driven by sort of these ocean patterns and coupled with the ENSO year led to an unprecedented situation. So it was the leading cause of primary forest loss in the tropics last year was natural disturbance, namely fire. It surpassed agricultural clearing, it surpassed every other form of tropical forest loss, right? So you can see this here, usually it's between, sort of 10 and 15%. And years that is drought, you can see that the previous ENSO year, 2015, but last year was really an outlier. Another way to look at this is to simply break down the causes. So here on the left, and this thing continues to evade me. There we go. So the leading causes of forest loss between 2002 and 2024 were large-scale agriculture and shifting cultivation. And in 2024, fire, in particular natural disturbance, was the leading cause by far. So this is a very big change. The losses were concentrated in the Amazon. Brazil had the vast majority of loss related to fire, followed by Bolivia, 12% of Bolivia. And this, of course, not only had to do with climate related to land use that were enacted in the country earlier in the year. These changes and these disturbance events don't happen without the context of human land use. Of course, particularly in the moist tropics, natural fire is a rare event. If the forest is intact and the understory has a certain amount, right? It happens as a sort of a mix of clearing forests for agriculture, the succession that happens naturally or with aid after that, and then planting of other crops such as grasses and so forth and shifting cultivation, right? In a recent analysis that used the Landsat record, Van Kutsen et al. Estimated, overall 17% of moist tropical forests are in some stage of regrowth, and that can be recovering from degradation or secondary regrowth after the cessation of agriculture. There's also, of course, plantations and all that, but it's a pretty significant proportion. And these are forests also that are many times not only degraded, but much more likely to be cleared. So there's been many studies that have shown the probability of clearing of second growth forests is very high when forests are young. And in a recent study also, there was a study showing the age of these second growth forests, and the vast majority of forests across the tropics are less than 5 years old. These are forests that are they have more than half probability of being cleared. And so we really need to make an effort to maintain these forests so that they can accrue the biodiversity benefits and the carbon benefits and so on that they can provide. And have characteristics that make them more susceptible to subsequent disturbance, whether it's heat, whether it's drought, whether it's fire. And as the forest recovers from the degradation or just after agriculture, the forests contain the kinds of species that are particularly physiologically vulnerable to drought, to heat, and so forth, right? So it's this deadly triad of vulnerabilities that develops in terms of subsequent. I'm not comprehensive, and I hope that I can talk to many of you about the studies that you have done and many other ideas and experiences that you have had in this. In the tropics is very complicated because it reflects many different things. It's not just drought and heat, right, and how that is changing, but it's also the patterns of rapidly changing land use and the scale of land use, things like road construction as well, and also shifts in human population and behavior. In terms of the drought, just drought as a driver of fire, right? We have seen in both the tropics and neotropics that the precipitation variability is increasing, the variation in precipitation variability is increasing faster than mean precipitation, meaning that we have more drier, sort of dry spells and wet spells. The ENSO amplitude is expected to remain, but again, the precipitation variability associated with ENSO is expected to intensify, amplifying these wet-dry swings in both monsoonal and tropical systems. And it's often the case for the Amazon. There's predictions of increasing drought pretty much across the board. For Southeast Asia, it's more variable, monsoon in that region. And for Africa, sort of the story is not as dire, even though it also has to be said that the data that we have for Africa is much more scarce. So the uncertainty is much higher for the predictions in Africa. In a very nice paper in 2019, Brando et al. Outlined the effects of the 2015-2016 ENSO globally on tropical forest carbon. But in doing so, they brought together a bunch of different drivers, and this shows very much a summary of the effects. So droughts essentially make the vegetation dry, right? They dry the air, they increase physiological stress for the trees, and they also, trees in response to this stress, shed leaves and biomass, which increases flammability if there's an ignition shorts, right? This pattern shows here that in the 2016 ENSO, right, there's two sources of mortality. There's tree mortality that is due to drought, that is shown here in green and yellow, and you see it happening all over the tropics, and also mortality associated with fire that increased, in all regions of the tropics. As I mentioned before, fire has to be understood in the context of variation in tropical forests in terms of the seasonality of precipitation, as well as the patterns of human land use. This is a summary of a 25-year study led by Annie Alencar, where they summarized what they had found in terms of fire occurrence and fire recurrence in the arc of deforestation of Brazil. And they looked at fire activity in transition, open, and dense forest. And these have different levels of precipitation, right? They're some more drier than others. And also they have different degrees of deforestation, with the open and transitional forests having higher deforestation than the dense forests. And what they found, not surprisingly, is that fire in the dense forest was primarily driven by ENSO, and it primarily consisted of small fires. However, in the open and transitional forests that were drier in terms of precipitation and also much more fragmented, forests were a lot bigger. And also, when they burned, they were more likely to reburn, which is what is shown here in this graph in the right. So this demonstrates very clearly that patterns of human land use by fragmenting forests and by increasing the ignition of the remaining forest lead to increased fire activity, and that has a positive feedback in the sense that degraded forest by fire are more likely to burn again. In fact, this is a very nice summary of what is going on in the Amazon by George Barlow in 2019. And we have come to think about fire as having sort of two broad classes. We have fires associated with deforestation that were, of course, in the news for many, many years. And these are intentional fires, both legal and illegal, that are set to clear land for agriculture or for either large-scale agriculture or small-scale agriculture. They are also used to maintain pastures in the Amazon, particularly in wetter regions, get really, really tall, and so they has to be cleared for. And also burning. What happens in a very dry year is that these intentional fires escape. And under very dry conditions, these uncontrolled fires enter the forest and lead to forest degradation, which in turn leads to more fire. And this also, adds to degradation and the probability of fire. So this is a sort of, again, a combination of compound disturbances that are all interacting to lead to fire regimes that are becoming less and less controllable. In fact, even though we used to think of deforestation as being associated with fires, this paper in 2018, they summarized decade. And what they found with this map on the dark red shows fire that is association activity, right? And the dark green shows fire that occurs in the absence of deforestation. And what they hypothesize is that this fire is driven primarily by of secondary forests, slash and burn agriculture, maintenance of existing forests, and the expansion. Again, once the land is degraded in terms of landscape use, this leads to more fire, not necessarily associated with deliberate deforestation per se, but simply as a byproduct of the activities of humans in the landscape. In fact, last year, which was, as I mentioned, an unprecedented year in terms of fire in the Amazon, if you look at the patterns of fire activity between 2020 and 2023, which is shown by that black dash, typically they occur in areas of recent deforestation, or consolidated deforestation, which is in about 3 years after an area is deforested, and far fewer fires in areas that were primary vegetation or secondary vegetation. In 2023, this kind of flipped. And so we see many more fires in primary forests, in primary vegetation. Forests are supposed to have enough humidity and be wet enough to stop fires, right? And this is not the case when you have a drought as severe as what we observed last year in the Amazon. And fires also determine the resilience of forests to subsequent drought. So in this graph, again, looking at 3 kinds of forests, short dry season and long dry season, this is by Leroux et al. Looked at the response to precipitation anomaly. So here in the bottom, you see the precipitation anomaly for 2015. And the top shows the EVI anomaly. So this is essentially an index of greenness, vegetation. And the relationship between the precipitation anomaly and the vegetation anomaly is higher with a longer dry season, which we would expect. But also looked at 3 different types of forests: mature forests that have been degraded recently in 2015 by fire, and fire that have been degraded point in the period of a study. And what they found is that forests, not surprisingly, forests that had been recently degraded had the highest anomaly. Fires that had been degraded at some point had the second highest anomaly, and primary forests had the lowest anomaly. So this fire activity also determines the resilience of vegetation to drought, to subsequent drought. All right, I'm gonna switch gears now and talk about cyclones. We are in a cyclone active area right now. And in fact, coming here, I got all kinds of warnings about this cyclone and that other cyclone and travel advisories. There's 3 areas in the world where, well, 4 areas that fire and cyclones intersect. The Caribbean, the South Indian Ocean, particularly the area around Madagascar, and then the South Pacific and some parts of the West Pacific. About 35% of cyclone-prone areas are wet forest, and typically we don't get, as I said, we don't get fire in wet forests because they are too humid for the fires to be important. When they occur, they are small and they go away quickly. These are also areas in which often we have dry forest and wet forest, at the regional scale, and they interact. And of course, agriculture. In terms of cyclone activity, even though this is a very active area of research and there's tremendous uncertainties globally, we expect to see three things: more frequent category storms, these are the most severe storms; maximum wind intensity, which is the major driver of tree damage. This was shown recently in a sort of meta-analysis; and weather storms. If we think about a fire or a hurricane affecting a forest or a fire affecting a forest in the context of a forest that is right next to a dry forest or a savanna or next to agricultural land, we can think about these events independently and jointly. So let's just kind of walk through that exercise. If a fire occurs only in agricultural land or in a savanna, it will not enter the forest because of the moisture conditions of the forest. If a cyclone occurs without a fire, it will simply just recover. The forest will recover, right? Now, the problem is if you have a cyclone and then you have a fire and dry conditions, then this forest will burn, right? And that leads to degraded forest. This is a picture taken 7 years after the passage of Cyclone Fanelli in Madagascar, and it delays the recovery. In fact, here in Central America, there was a study done showing that the recovery of a cyclone that occurred 3,300 years ago took over 500 years because of subsequent repeated fires. These are both natural fires and fires set by humans, right? Which in some cases we can't detect the difference here. But this is essentially when the line here shows the sand layer, which is usually a sign of a cyclone, and it's been used to evaluate cyclone activity, and then sort of repeated fires that delayed regeneration. This also happened after the passage of Hurricane Joan in this area. Over 90,000 hectares of swamp forest burned after the common. So I'm going to talk about a different kind of wind. So this is cyclonic wind, right? We also have other kinds that we'll hear all this term. So these are events that form due to the instability of the and to create thunderstorms, right? And those are predicted to increase because we expect with higher temperatures, increasing atmospheric instability, and changing humidity profiles. These events, the work of several people have shown that they account for 50% of tree mortality in the Amazon. And they're very easy to see. So you see this picture here, this is from our work in Ucayali. Before and after, they are very easy to see. You can see how the wind moved, the trees fall in a certain direction, so they are easy to map and see. So one of the challenges with these events is that it's very hard to connect using any kind of mechanistic model the relationship between these blowdown events and wind mortality. So in a recent paper, Feng et al. Mapped over 1,000 wind throw events in the Amazon. And then they connected them to this metric of atmospheric instability that is called convective available potential. And they showed the relationship between CAPE and wind throw activity at the scale of the Amazon. Now, unlike wind throw events, which are very hard to predict using any kind of Earth system models, CAPE can be predicted from Earth system models. So what they did then is to run down, the latest CMIP models and say, what would be the effect of a changing climate that we expect at the end of the century on CAPE and therefore on wind throws? What we found is that there was a much larger area that would be affected by these events, and they predict an increase of 43% in this blowdown activity in the Amazon. This is not just the future, but in a follow-up paper, they show that this has already happened. So the number of wind throws between 1985, they went back through the Landsat archive and mapped a crazy number of wind throw events, hopefully with the aid of artificial intelligence, and the wind throw area and the mean afternoon CAPE, showing increases across the board between 1985 and 2020. So we were working in Ucayali in mid-2010s, and we were studying something completely different, succession and fire. We had set up these very nice plots, we meaning my former student, Naomi Schwartz, and all the plots were hit by one of these wind throw events. And of course, you get lemons, you make lemonade, right? So as you can see there, we mapped this area. There was a combination of palm oil, oil palm, old growth and second growth forest. And we got interested in the effect of fragmentation on wind damage. This is a landscape that is highly fragmented, and fragmentation changes circulation patterns, and it creates strong adventitious winds. And of course, the trees that are on the edges of those fragments are not adapted to wind disturbance. So what we found is that using a number of different fragmentation metrics, including the distance to the edge, the size of the fragment, using this changing, it's a satellite-derived metric for synthetic vegetation. And that this effect was stronger for old-growth forest, even though second-growth forests had more damage because they were generally more fragmented. And in a previous estimate of the effect of this wind throw in total carbon loss in the Amazon, and our estimate is that if you include fragmentation, at least for our region, the area of study, not across the Amazon, it increases the carbon loss by 50%. So this is a very significant change. And also, I assume accidentally, there was another study, famous study in the Amazon, is a study, experimental fire study. And they have three treatments, right? Control, they burn every year, or they burn every 3 years. And they were hit by one of these blowdown events. And so what happened, the major amount of damage was uprooted and snapped. The most likely trees to be damaged were the trees that had been burned, particularly the trees that were burned every 3 years. And the majority of these trees that were damaged died. The larger trees, particularly for those in the treatment that was burned every 3 years, and those closer to edges were more susceptible to damage. So we have an interaction now between, I don't know how many things, I lost track, but these are, you get my point, that there's a lot of interactions between these different disturbance events. And I want to switch now just to Puerto Rico and talk about what we're doing. So for Puerto Rico and for the Caribbean in general, the predictions are that we're going to get more severe hurricanes and more drought conditions. So in terms of resilience, nature in the forest favoring some species, right? And the species that hurricanes favor tend to fall into the two categories: resistant, and in our case, this is a palm that is everywhere, or resilient. This is a particular species after a hurricane, after the canopy opens, right? So, we had been doing some work on drought. We, meaning Chris Smith-Martin, that is sitting in the audience there, who led this project. And we looked at the data that we had from the 16-hectare plot to see changes in the abundance of different species after the Hurricane Hugo that happened in 1989. So we saw 3 species that became really abundant after the hurricane. The palm that I mentioned, which is highly resistant. Cecropia, that had a kind of like a boom and boost cycle there, but also became very abundant. And then one species that is a late successional species, I'll go into that in a minute, that also increased in abundance, is the dominant species in the forest. Well, we had done some work on the drought resistance of these species, and we had evaluated the resistance to embolism, which is a metric of, sort of hydraulic resistance, vulnerability to drought. That these 3 species were not at all resistant to drought. And in fact, resistance to drought did not align whatsoever with successional status, which is not what you might expect. At the forest level, we were able to show that after the hurricane, the vulnerability of the forest as a whole decreased substantially. So now, We are conducting an experiment in Puerto Rico. It's a threefold exposure experiment that we started after the passage of Hurricane Maria, with very heavily instrumented trees, trying to understand the patterns of growth and recovery and physiology of trees that had been damaged by hurricane. And I'm going to plug into, and we can evaluate the degree of damage using repeated LiDAR flyovers over the site. And Rebecca Montgomery is going to give a summary talk on the experiment, and Laura Boschotten will talk about our preliminary findings. So if you have, so I'm going to talk now about, well, what do we call this, or how should we move forward with this crazy amount of interactions? So there's 4 areas need our attention. First is the development of some kind of standardized framework for studying disturbance. Second is to understand much better the long-term trajectories of forests and ecosystems, using both data, things like plot data, but also long-term data, paleo data, and models. We need early warning system for tipping points. And then I'm going to talk briefly about socio-ecological impacts and feedbacks, because that's the subject of, that's a whole conference or several conferences in itself. So what is the issue with developing standardized frameworks for study? It's very difficult because each event is different. It occurs at a different time. We talk about this issue of contingency, right? It occurs sometimes at sequence matters. Often we don't have pre-treatment data in Puerto Rico, so we have pre-treatment data because we've been there 30 years. But I can tell you that the study that we did in Ecological was not planned. I'm pretty sure that the fire experiment and the interaction between wind and fire in the fire experiment in the Amazon was not planned. And so we end up with this sort of accidental approach rather than a systematic approach about how we're going to study disturbance. I also think that because it's such an idiosyncratic subject, theorists kind of shy away from it. There is no theory of disturbance, right? I mean, there's the successional niche hypothesis, the intermediate disturbance hypothesis, but we need like some kind of meaty or something. And again, the theory development is hindered by this issue that it's very event and it's very contingency driven, and theories tend to, or when they work on these subjects, they work on systems that are highly controlled. So what are we to do? Well, there's 3 approaches, I think. One is remote sensing, another one is collaborative networks, and the third one is co-opting existing data sets, which we're already doing. This is a paper that came out last year, which I thought did a decent job of starting something. And what they did is to map disturbances across the world using Landsat. And they were interested in the spatio-temporal patterns of disturbance. So how big are they? What shape do they have? And how long? And what they found for tropical regions, where I also have to say that the data set that they used was from 2010, so neither of the recent ENSOs are included in this analysis. They tend to be small, right? So this is what they call small isolated. Those are disturbances of about 0.2 hectares. And some are clustered, right? So these are just events that join together, about 1.2 hectares, but not very big. In other areas, you see, is quite different. And also, they divided them between disturbances that occur inside of intact forests or outside forests, right? So this gives us an idea of what is happening inside of these big forests. Are they small disturbance dynamics? Is it a small scale agriculture, right? But that would be kind of like some way of thinking about how to map. And there's been a lot of work done on mapping disturbances. I just wanted to show a global evaluation. In terms of trajectories, right? There's the Second Four Network, which has been doing an amazing job of tracking and writing all kinds of great papers about succession. And there's, in fact, I think a session after this one on succession that I'm sure will be very interesting. But how many studies are out there of demography after succession, right? So we did RCN and we looked, it was published in 2016, but we found 112 studies of post-disturbance demography in second growth forests. And these are forests that were growing after storms, fire, etc. And found, well, as usual, the majority of studies were in the neotropics, but also, not surprisingly, that the majority of studies, looked at mortality, right? And the three numbers there is, the first one is a positive effect, the middle one is a neutral effect, the last one is a negative effect, right? The majority of studies were done on large trees, and we looked at mortality. Why? Because if you don't have pre-treatment data or pre-event data, that's something that you can look at, relatively straightforward, right? We had much less information on the smaller tree sizes, which are, of course, very critical to the future of the forest into the long term, right? In a paper in 2020, this is showing the same story, but global level. I mean, we just don't know, particularly things like reproduction. What is the effect of disturbance on reproduction? Our understanding is so minimal, and yet it is absolutely critical for the future of the forest, right? So we need more information on demography. And as we think about these big networks, forest plots, forest geos, SICOM4, how do we incorporate the study of, because this has to be done, right? I'm not out of, so this disturbance on tree recruitment, essentially on demographic trajectories, right? Created ultimately by the landscape context in which these forests exist, right? So the climate that they have, the environment in which they occur, the history of disturbance that they have. Oh, okay. Okay, great, thank you. So one approach is to look at paleo data. There was a paper just came out in 2014 that looked at 71 dated studies of changes in pollen over 20,000 years that were attributed to disturbance. And they found America and Africa relative to South America and Asia. To this idea, of course, that these forests that have grown in a region that has a greater rate of disturbance also have a greater rate of resilience, right? Although this may be limited, but this is an interesting study. There was another study by Van der Schande et al. In 2022 that summarized studies also of pollen records at both high and low elevation forests that found that disturbance increased, the species that had certain characteristics like big leaves, small seeds, rapid growth, and so forth. And the fires led to more stress-adapted species. We need more of this stuff. We need more, the sort of interaction of paleo work with the. Another approach for studying or predicting the future of these forests, of course, is models. And we ask a lot of things of models. And there's been tremendous progress in being able to map some of the things that go into these dynamic vegetation models and system models. So we can do a pretty good job mapping field moisture, soil moisture, canopy height, biomass, and all of these things, right? But at the heart of all of these great remote sensing is the vegetation and what it does, right? So generally, models, these are what you see here, the forest PFTs, right? And there's like one of two approaches, right? Either you sort of make these, assign a species to a PFT in a somewhat arbitrary fashion, even though, of course, there's some science behind it. Or, there's been a very promising developments in demography in the past few years, and you may have been follow the idea of to understand the demographic trade-offs that a species experience and to use some kind of continuous approach to be able to display these demographic trade-offs and put them into models, right? So this is the work of Nadia Roger that started the work, I think, with BCI, and they found these two trade-offs. Essentially, the trade-off between growing fast and survival, right? And that was also related per capita recruitment, and a trade-off between versus recruitment. So these are trees that can grow very fast, they get very tall, but they recruit very poorly versus the ones that stay in the understory and recruit all the time, right? And this seems to work pretty well. And in the study of Kambach et al., they applied this study to 14 forests in the forest geo network. And the only hurricane-affected forests, Luquillo displayed different trade-offs with the stature, not surprisingly, right? But then this begs the question, this is the future for, sort of incorporating the variation in the species life histories into these models, which is the only way that we're going to get this right, by the way, then how does disturbance shape these demographic trade-offs? And what are the key traits that should go into these models? So many years ago, I looked at this in Puerto Rico, and I found that there was a very clear trade-off between of trees to the increase in light availability that happens after a hurricane, and that has to do with increased growth, increase in fecundity, and so forth and so on, and the proportion of stems for basal sprouts. And it is generally known that sprouting is a common species response to chronic disturbance, right? Fire, particularly in dry forests, right? So, but sprouting, even though there's a couple of efforts underway, is very messy, and it's hard to incorporate into these types of models. For fire, there was also a recent study led by Carla Staver that relationship between variation in climate with the idea that you would have thicker bark in dry forest and forest, and this is what they found. And they also found that thinner bark translated using a combination of plot data into higher rates of fire-driven mortality. There was a study that Lawrence Portland in Bolivia comparing dried and wet forests that found that this was not the case in this particular site. And what they found was a relationship with the stature. So bigger trees had thicker branches. And there was, again, the hypothesis that perhaps trees with thinner bark and shorter trees survive by sprouting, right? So again, a return to sprouting as a potential mechanism to withstand disturbance. So anyway, we need to do a better job of incorporating disturbance into models using some kind of approach. And this perhaps also some more subtle. This is one of my favorite papers ever, so I had to talk about it. This is a study, again, accidental. So there's this garden in Miami, the Montgomery Botanical Garden, that has the biggest collection of neotropical palms. And they looked at the mortality of different palms depending on the provenance. And what they found was that palms had much lower rates of mortality cyclone-free areas. So again, this is a subtle adaptation disturbance, which also calls for thinking about what are, I mentioned before that, of course, the species, the biota adapt to the disturbance regime in which they evolved, right? This recent paper did a very nice job of sort of mapping, in terms of wind disturbance, how we may think about different regions, right? So they start with resilient regular disturbance. These are forests that are mapped here in orange, so some parts of the Caribbean that have very frequent disturbance. They recover between. Then we have systems that are dependent on disturbance, and that means that they would do completely different if this disturbance didn't exist, right? And those are a different class of forests that are in that area. And then there are forests that are vulnerable because they have not been exposed to this disturbance before, right? So it would be really cool, kind of big map and saying, where are the areas that are really going to be hit multiple disturbances that have not experiences, and we don't expect the species in these areas to be adapted to these types of disturbances. So I want to return now in this context to this idea of tipping points, right? So I mentioned before that this interaction of disturbances can lead not only to a delay in recovery, but to tipping points, that is the movement to an entirely different ecosystem, right? And it would be nice to know what those areas will be. And there's been a couple of different approaches to that. In a very nice paper, Bernardo Flores et al. Last year did this analysis for the Amazon, and they looked at using an additive approach of how disturbances are affecting the Amazon, right? And they mapped them. So they looked at temperature increase in the last 40 years, ecosystem stability, that's whether that region area between savanna and forest, repeat severe drought. It would be nice to add the recent drought there. Roads and fires, the governance status, whether that is inside a protected area or indigenous area or not. And then based on that, they develop a map of tipping potential. right? And that was, this could be done, of course, a much smaller scale using different metrics. But what do we think is the vulnerability of these areas to repeated disturbance, right? There's also this other set of analyses, which I'm still kind of scratching my head about, but which are here, and this is already happening in Brazil, certainly, but we can do a better job of it. And then we need to provide social services and training that allow people to remain in rural landscapes and manage the disturbance. There's some great efforts already ongoing with fire brigades in Brazil, in Indonesia, but training on things like fire breaks, prescribed burning, things that we do in the temperate zone as a matter of course, right? There's very limited funding for that, sadly, but this is something that could greatly help in managing the increasing risks that disturbances bring to forests and to us. Thank you for your attention, and I want to thank all the collaborators, students, and colleagues that have taught me all kinds of things about these topics over the years. Thank you.
Thank you very much, Maria. We have time for 2 questions.
Thank you very much, Maria. Can you hear me? No.
Yes.
Okay. Thank you very much. It's a very nice talk. But I want to, to give attention to another potential risk of forest disturbance, that is the proliferation of plant diseases in disturbed areas. My own experience in southern Mexico and in the Amazon, central Amazon, is that forest disturbance increases the incidence of plant diseases, mainly by fungal pathogens. I don't know if you can say more about this.
I think we know very, very little about plant pathogens, and in the tropics. I mean, in the temperate zone, this has been well established a long time ago. And I think that there was this idea that perhaps the diversity of forests and species would protect us from, sort of pathogen damage. I don't think that's the case. This is increasing globally. I did not look at pathogens on purpose, because I know that this is an incredibly complicated subject, but this is what I meant. I mean, I didn't mean to be, sort of extensive I was just trying to provide some examples, but this is another area of research. Invasive species. A lot of the fire in the Amazon is driven by pasture grasses that were introduced for cattle there that are not native, that are incredibly resistant to drought, right? So we could go on other disturbances, but thank you for bringing, and I would love to hear what you found on this.
One more question.
Thank you for a really masterful talk. You started out by making a distinction between natural and anthropogenic disturbances. Now, in terms of policy, this is a huge distinction, because policymakers tend to say, well, if it's natural, it's nature, it's God or whatever, we can't do much about it. But of course, as your talk showed, this distinction is increasingly blurred, because these effects cross this boundary. I'd like you to ask you to comment on this, please.
Yes, thank you. Thank you for that very eloquent way to say something that it's been on my mind, but I didn't say explicitly. I think in some cases it's pretty clear. Like, for instance, fire, right? Fire does not exist without human disturbance. Somebody has to go and start an ignition and cause and degrade the forest and so forth to get the kinds of fires that we're getting, right? With other areas, I think is more complicated, right? The hurricanes, for instance, right? We know when we degrade the coasts, this becomes a bigger issue. I think where there's a very high economic risk, there is policymakers get interested in this. So I'll give you an example, and because I've read about this a fair amount. The development of, sort of development in general, by land clearing, mangrove clearing, risks to coastal property, is of interest to many people, policymakers, because it has a very clear effect on, sort of damage, economic losses, and so forth. I think assigning economic losses to disturbance events is kind of like one first step. And I don't think that we have a good grasp of those losses, for many areas of the tropics. When you look at, there's a data set that is essentially ZenCRA, and it's a database of reported disasters, right? And they keep track of all the disasters, how many people were affected, how many people were killed, what is the estimated damage. And those numbers have been increasing, right? But I think to get policy makers involved, we have to sort of show that there's an economic impact or an impact on lives, right? And at that point, I don't think it matters whether it is one or the other, but they're inextricably linked, particularly when it comes to risks to humans.
Well, thank you very much, Maria, for a wonderful. Two more housekeeping announcements. One is that if someone is feeling ill, they can go and try a COVID test, a free COVID test at the registration desk. And another one, there's still places to go to the Geoparque. It's a wonderful place. If you don't have anything to do on Friday, I recommend you to go. Also, if you want to book a ticket for that, go to the registration desk. And thank you very much. Muy bien. Sí, muy bueno. Muy comprehensive.